Hello. So, we will continue our discussion on spatial analysis. We were discussing on some aspects of spatial data mining and different aspects of spatial data mining, what are its importance and how it help in doing prediction and analysis and type of things, right. So, today we will continue with that discussion and see some more features specifically that which are more predominant for spatial context rather than our non-spatial context, right. So, one is, as we have as you if you recollect, we discussed about patterns, spatial patterns, right. So, that finding some interesting not but non-trivial patterns from the data sets, right. It is space time data sets or spatial data sets, right. So, something which is non-trivial. If it is a trivial, that those patterns are not interesting, right. So, those patterns are like common patterns. So, so for any, if we little go back to our initial part of this course, so we discussed about spatial data models, right. So, looking at the spatial data models again, whatever we want to do analysis, we definitely requires a data model which encompasses all things. We require definitely the spatial SQLs and spatial database which helps us in extracting data, not only that maintaining of the whole spatial database and so on and so forth. So, the spatial data model concepts is there. So, what if you just recollect, there are entities, categories of distinct, identifiable, relevant objects or things. There are attribute, properties, features or characteristics of the entities, like attribute of the entities, instances of the entities, individual occurrence of the entities, and relationship, interaction or connection among the entities, that is the, like for example, neighbor. State A or country A is a neighbor of B. So, that is a relationship, right. So, we have also seen different types of neighbors. We are not going into much deeper into that, those already we discussed. So, there are issues of degree of, when you talk about relations, degree, that number of participating entities, or cardinality, number of instances of an entity in an instance of relationship, self referencing, interaction among instances of a single entity, right. So, instances of a relationship, individual occurrence of the relationship, right. So, instances of a relationship, individual occurrence. So, that means we have a generic definition, instantiation of that, say particular entity, particular relationship and this. So, when we talk about pattern families in entity relationship model, relationship among entities, that is for example, neighbors, value based interaction among the entities, like how much they are related. So, we want to have some quantifying. So, I say that these two are more close neighbor than that two, between A and B are more closer than A and C. So, that should be a way to quantify those things, right. I want maybe the region A, region B, if I say they are more closer than this, my definition of closer may be the distance of the centroid of the things, that may be a way of the thing. So, that means the closer type of things, right. So, what is there, that is data models, and there are entity relationship models, like to find for these pattern families in the entity relationship model. So, these are the core of the things which are should be there. So, families of SDM patterns, like spatial data mining, common families of patterns, as we have seen that location prediction is one of the very predominant, spatial interaction and hotspot, right. So, location prediction is determination of value of a spatial attribute in a entity by values of the other attributes of the same entity, right. I can find out that that the particular event or particular activity where it is likely to be the next located, right. So, that is special attributes of an entity by a value of other attributes of the same entity, I want to predict that location. Spatial interaction is a n-array interaction among the subset of the entities, like if there is interaction. So, it can be n-array interaction among categorical attributes of an entity, right. I can, instead of subset of the entities, there can be a categorical interaction among the category. And hotspot is self-referencing interaction among the instances of an entities, right. So, we want to find out that particular hotspot, like we are looking for crime hotspot, etc. So, the number of occurrences are much more in that particular crime and region to the in a particular region than the in other regions. So, something may be noted that other families of patterns may be defined, like it based on your requirement you can define other families of pattern or particular domain requirement or application requirement. And SDM per se is a growing field which should accommodate new families of patterns. So, that so to say that the spatial data mining framework should be able to accommodate these new families of pattern. So, unique properties of spatial patterns. So, there are some of the unique properties of spatial patterns which basically distinguish it from other non-spatial patterns, like items in a traditional data are independent of each other, right. Items in a traditional data sets are independent of each other, right. Like say if you have a student database, right. So, say even different tuples, I cannot say there is an inherent relationship. They may be in the same class and type of things, but the different values of the item sets are independent of one another, right. Like marks of a student is independent of the marks of the other students, right. That we may try to find out with respect to that if the teaching quality is high and type of things and like that, or bank account numbers, right. The amount of balance of a one customer is independent of the balance of the other customers, right. So, there is what we say items in a traditional data sets are independent of each other, right. Whereas, properties of a location in a map are often auto correlated, right. So, there is a inherent thing called auto correlated, the same thing correlated to the same type of object, right. Like temperature of a region cannot be independent of the temperature of the nearby region, right. So, it is there is a influence on the thing, or rainfall of a region is somewhat dependent on the rainfall of the other region, right. Of the nearby region, right. Temperature of Kharagpur may not be directly influenced by the temperature of say somewhere in Pune or somewhere in Bangalore, but temperature of Kharagpur is definitely have some relation of the Medinipur. So, this temperature thing is auto correlated, right. So, traditional data sets deal with simple domain like numbers and symbols, right, whereas spatial data types are more complex, right. It has a shape and other type of things. So, there is not simple domains. Items in the traditional data set describe discrete objects, right, whereas spatial data sets are mostly continuous, right. So, there are differences, and there is a first law of geography given by Toppler, which says everything is related to everything, but nearby things are more related than distance things, right. So, any phenomena which is any spatial phenomena or any geospatial phenomena are related to one another, right, but the nearby things are more related than the distance thing, right. So, that is why we say that the temperature of Kharagpur is influenced or is more related to the temperature of the nearby places, right. So, it is or different type of thing, something some sort of a, if some seasonal disease is happening in Kharagpur, it is likely that nearby things, it is not that the far things, but there may be some relations, but there is more you go the distance, the relationship is become weaker. So, people with similar background tends to live in the same area, right, like we heard about hear about that HIG flat, MIG flat, LIG flat, low income group, high middle income group, etc. So, why they are mixed in a particular block or type of things, because it is seen that people with the same background or same income group are trained to in the same area. Economy of nearby region tends to be similar, right. So, that it is there. Changes in temperature occur gradually over space time, right. So, if we say the temperature of a particular region, it is gradually over the space it changes, right, and also over gradually over the temporal scale also changes. So, these are things which comes out of that first law of geography by Tobler. So, we have mapping techniques to spatial pattern families. So, that several techniques to find out the spatial pattern families, right, how to identify these spatial patterns. So, it is not that straightforward or not that that we can use that straightway all the techniques which are there in the traditional pattern analysis or non-spatial data analysis, right. Choose of technique depends on the feature selection, spatial data, etc. So, which techniques will depend? Spatial patterns families versus techniques, location prediction, like for location prediction we use typically classification, function determination and type of things. Interaction, what we do, correlation, association, co-location type of things, right, when we look about interactions of the things. When we find out the location, then we want to classify and function determination, that what should be the next predicted location and type of things. When we look about the hotspot, we look for clustering, outlier technique, that things like that, when we look at the hotspot type of things, right. So, what we see that finding different pattern techniques, we need to deploy different type of techniques or methods or approaches, right. So, here the focus is on our this spatial problem, right, even though these techniques apply to non-spatial data set also. So, whatever the techniques which are talking about, these are applicable, so many of them are applicable to non-spatial data set also, but here we mostly try to deal with spatial data into consideration. So, one things which is coming now and then, what we say spatial autocorrelation, right. So, before we go other type of techniques, we thought that it will be nice that we can have a overview of the spatial autocorrelation, right. So, what does it mean, what are the typical or standard techniques to calculate? There are different type of techniques and there are different mechanisms to do that. We want to see that what are the different techniques, how it can be calculated. So, we want to see that what is the spatial autocorrelation per se, why spatial autocorrelation is important for our all the spatial analysis and stuffs like that, how to measure spatial autocorrelation, maybe one or two examples. So, when we talk about spatial autocorrelation, is a special property of geospatial or spatial data, right. So, spatial autocorrelation is a typical property of spatial or geospatial data. It is a statistical test of it is a formal property that measure the degree to which the near and distant objects are related. So, it is a formal property that measure the degree to which the near and distant things are related, right. So, it is a statistical test of match between location similarity and attribute similarity, right. So, this is important. So, it is a statistical test between the location, that means the where the coordinate wise things are there, and the attribute value similarity, right. So, it is a thing, and it is a property that is often exhibited by variables which are sampled over space. So, and it is a property what when we sample the things over space, it comes into play. As in our spatial context, this is very much there, the things are sampled over space, so the autocorrelations come into play, and it is based on as we have seen in the last slide, Tobler's first law of geography. Right. So, just to repeat, the basic philosophy of the Tobler's first law of geography tells that all places are related, but nearby places are more related to than distant places. So, what it says that the all places are related, but the nearby places are more related than the distance places, right. So, that is if we look at temperature, those will be more related, which are next to the region, but definitely there may be relations with the distance things also. Example, like temperature values of two locations near to each other will be similar, will be more similar or more related than the temperature of two locations at a far away distances. So, this is the things which I am comparing, these are the different things. So, these are more closely and these are far away stuff. So, spatial if we look at the spatial type of spatial autocorrelation, like types of spatial autocorrelation. So, one is positively correlated, right. So, that means it is in a neighboring areas are more alike and type of things, or it can be negatively correlated, like neighboring areas are more unlike. Here if you see there is a neighboring, and it can be a random correlation, right. Pattern exhibit no spatial auto correlation, right. So, there is no spatial autocorrelation. So, what these are things are not you cannot predict that what is going on, which are it is nearby, etc. So, this is positive correlation, negative correlation and random autocorrelation. So, these are the three type of spatial autocorrelation traditionally. Now, why this spatial correlation is important? Most statistics are based on assumption that the values of observation in each sample are independent to each other, right. Most statistics are based on the assumption that the values of observation in each samples are independent to each other, right. If the samples were taken from nearby areas, then positive spatial autocorrelation might violate this, right. So, though the statistics based on the assumption that the values of the observation each samples are independent. When we take samples in a typical statistical analysis, these observations are independent. Whereas, if the samples were taken from nearby areas, then positive spatial autocorrelation may violate this. So, like this is a particular map of the things, and then we say that to measure the strength of spatial autocorrelation in a map, we want to given a map, we want to find out that what is how much autocorrelated things are there. Test the assumption of independent or randomness to explore whether there is any clustering pattern in the data or it is just a random data, right. So, this is our basic goal thing, and if we recollect that our few slides back or the previous lectures, these are the things which dictates the how these SDM patterns will generate, right. So, this is important. So, autocorrelation makes us a foundation for doing any type of spatial analysis or spatial data mining type of activities. Measuring spatial autocorrelation, there are typically 3 steps. Find out which areas are likely are linked to one another, choose a neighborhood criteria. So, which areas are linked. Secondly, assign weights to the areas that are linked, create a spatial weight matrix, and run statistical tests with using weight matrix to examine spatial autocorrelation, right. So, one is that choosing a neighborhood region, neighborhood criteria, assign weights to the areas that are linked, that create a spatial weight matrix, and run statistical test using weight matrix to examine spatial autocorrelation. So, these are the things which are there. So, neighborhood criteria, so it is contiguity, common boundary, maybe a neighborhood criteria. Distance k nearest neighbor, distance band, how many neighbors to include, what distance do we use, and type of things, right. So, like here if you see, if particular this region, so these are my distance from the say centroid of the different neighborhood region. Now, I need to define that if I my D2 is my consideration is my neighbor, then maybe 1 or 2 may be touching, these are the things, where if it is D1 is my neighbor, then I have few more neighbors, right. So, it looks at that defining the neighborhood criteria is important, that how we want to look at the things. Contiguity, adjacency, sharing a border or boundary or point, right. So, adjacency is things for a regular polygon, it can be this sort of things, or those who are accustomed or those who have played chess, they know that these are the things, the movement of a particular rook, right, either vertically or horizontally. So, this type of things, if it is my search space is just this 4, then we say this is a rook case, right. So, I want to find a neighbor considering this rook case or type of things, and in a again in a chessboard the bishop movements is diagonal. So, I can have a bishop case, or it can be a queen case, right, where given a point all surroundings are the queen can move in all things, either diagonal or vertical or horizontal. So, this is a queen case. So, for irregular polygon, all polygons that share a common boundary border or have a centroid within that particular circle of search or circle defined by the average distance up to the centroid of the polygon that share a common boundary, right. So, that can be the things, right. So, we can have different type of scenarios like this. Now, spatial weight matrix, weight based on contiguity. If a zone J is adjacent to a zone I, interaction receives a weight 1, otherwise it receives a weight 0 and essentially excluded. Like A to A, there is no as such, we are not considering that they are things the same region. So, 0. A to B connection is there, A to C is there, A to D is there, A to E no, A to F no. So, there is no contiguity, and similarly I can create like C to A is there, C to B is there, C to C is not considered, C to D, C to 1 and so on and so forth, right. So, this is the different what we say weight based contiguity or given 1 0 type of values in the line. So, weight based distance you we can have different type of matrices, like use a measure to actual distance between the points or between the polygon centroids, right. If it is a points or polygon centroids, find the actual distance. So, there can be different way of calculation. One is that inverse proportional W I j equal to 1 by d y, that will be captured like d I j. That means, if I say these two centroid, this and this, so their weight is calculated the inverse distance, right. So, in other sense, if it is if we consider this weight for influence, so more the distance it is, the influence will be less, right. So, inverse distance is a very popular. Inverse of square distance is also popular, instead of only d I j 1 by d I j square. Negative exponential e to the power minus d e to the power minus d square, or length of sharing boundaries, right. So, I can have a length of the sharing boundary. So, length I j divided by length I can be the thing, right. So, this can be different way of matrices. So, what we are trying to see here, there are spatial weight matrix and try to see that how I can have a quantitative value of these matrices, which can be used for my spatial analysis. Now, what I want to find out, that how these things influences, if there is a effect here, how it will be affected there, if there is a congestion in a region A of a say part A or the a particular region of a city, how that will be affected in the other region of the cities, right. So, how it influences the things, right. So, one way is that if I see this type of data and distances etc., I can try to predict type of things, right. So, even there are different type of parameters may come into play, that how the regions are connected, if it is a traffic movement, if it is a say flooding of the things, right, how things will be there, right. There are different patterns, different parameters like elevation and landfall level and type of so on and so forth. Nevertheless, things are, I want to calculate this some weight based on the distances. Now, there are several statistical techniques to examine spatial autocorrelation, right. So, we have various statistical tests for autocorrelation. The statistical state for performance of spatial autocorrelation, there are some of the global tests like taking the whole of the region. One is Moran's I is one of the very popular, and another is Geary's C, this is another scheme. And local test, there is a test called LISA, local indicators of spatial autocorrelation. So, local Moran's I is the local test. There are other tests like chi-square test, joint count, statistics and type of things. Out of this, what we see that Moran's I, local Moran's I and joint count statistics, these are popular and can be applied to spatial data sets we are dealing with, right. So, this is the things we are looking at. So, this is global Moran's I's expression, how to calculate, that is the product of the deviation from the mean for all pair of adjacent regions, right. So, a measure of variance across the regions. So, this is things, or sum of weights counts of all the adjacent regions that can be, these are the different components. So, the Moran I is calculated in this fashion. So, n equal to number of regions, x bar the mean, xj is the variable value in the particular location, jxi, and wij is the weight index location from of I relative to the j, right. So, these are the different parameters. So, Moran's I typically ranges from -1 to +1. Indices close to 0 indicates random pattern. So, if it is a close to 0, then it indicates random pattern. Indices towards +1 indicate a tendency towards the clustering, right. So, if it is a, if the Moran's I value is more towards +1, so there is a tendency of clustering is there. If it is towards more towards -1, indicate tendency towards dispersion or some sort of a uniform distribution type of things, right. So, there is no specific inherent clustering into the things. So, if the value is towards +1, then there is a inherent clustering, right. So, indices towards -1 indicates there is a dispersion or uniformity into the things. That may not be very interesting, depends on that how what the application area is there. So, this is a one measure to look at the things. So, there is a local Moran's I, which is some variant of the things. Local specific statistics used to determine if the local autocorrelation exists around each region I. So, clusters, hotspots or heterogeneity. So, it is there. So, it defines a nearby region, right. So, it defines a particular buffer zone. So, I is the point where we calculate I, neighborhood specified by the weight metric. So, it is the neighborhood zone. So, it is this is where in this case is a global taking all consideration, it is a local taking the consideration of a particular neighborhood region. And we have a joint count statistics for things. So, there can be different type of variation. One, this is a for positive autocorrelation, and there if there is a fully uniform or spread like this, there is no autocorrelation, and if it is there is a negative autocorrelation like. So, there are three type of things here. It is a sort of a binary image, we can calculate different rook case. So, this is with the rook case and queen case. So, different type of values calculation we can do, like here what we say joint of BB, that is black to black is 27, white to white is 27, and joint count statistics of black and white is 6, right. That is easy to calculate. So, 27 is, if you see that how much this black to black sharing is there are 27, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 1, 2, 3, 4, 5, 5 into 3, 15, 15 plus 12 is 27, right. 6 is, you see 1, 2, 3, 4, 5, 6, 6 the things. Similarly, if this is the rook case, rook can go only in the horizontal and vertical direction. Similarly, we can calculate it by queen's case, and for all these autocorrelations, right. So, for binary 1-0 category data only shown in black and white requires contiguity matrix for polygon based upon portion of joins between the categories, for like total 60 for rook case, 110 for queen's case, and type of things. A join age is classified as either WW00 or black black 11 or black W10 type of things, right. So, these are the way we calculate. So, for today's discussion, what we have seen, that we tried to look at that how the spatial patterns can be quantified. More specifically, we tried to see that one of the important property of spatial data mining or any spatial analysis is the spatial autocorrelation. So, how what it is, why it is important, how to calculate. We will be continuing this discussion in our subsequent lecture. Thank you.